In this lesson, you will learn about finding limits graphically and numerically.
Hello, everyone. I'm Professor Morvan, and I look forward to helping you learn about limits. You will soon discover that evaluating a limit is a very different process from evaluating a function, like you did in your algebra classes. Evaluating a function names a single point on the graph at the exact location of x equals c, whereas evaluating a limit analyzes infinitely many points on the graph as x gets closer and closer, but never equal to c. Now, we will need to do a bunch of calculations in this lesson, so you can either use your handy-dandy slide rule to do those calculations, might take you a while, or you'll need to go get your TI-30 X2S calculator and use that. So let's get started.
First up, we estimate a limit numerically. To do that, we create a table of values for f of x as x approaches a given value from both left and right sides. Now remember that f of x is another name for the y value. In this example, we have to sketch the graph of f of x is equal to the quantity x squared minus 5x plus 6 over the quantity x minus 2. Now first off, let's try to evaluate f of 2. Because substituting 2 in for x would give us a 0 in the denominator, we know that f of 2 does not exist or is undefined. So you can either use the symbol for undefined, or you are allowed to write DNE for does not exist. Now let's try to sketch the graph here. From our days in algebra, we recognize that this numerator can be factored. To get an x squared for the first term, we know that's going to be x times x. To get a positive 6 for the last term, we know that both factors would have to be positive or both factors would have to be negative. Since the middle term is negative 5x, then we will choose a negative 2 and a negative 3 in order to get that positive 6. Because negative 2 times negative 3 is positive 6, but negative 2x plus a negative 3x gives us the negative 5x. Now here we still have x minus 2 in the denominator. Now remember from your college algebra days, when you have a rational function with a common factor in both the numerator and denominator, that means there's actually going to be a whole at x equals 2. Now we can find the y value if we temporarily ignore this common factor. Remember that we can't cancel it, or we would change who f of x is. If we temporarily ignore this common factor, plugged in the 2 here, 2 minus 3 would give us a negative 1. So that tells us that the graph of this function, which can be written like this, is going to have a hole at the point 2, negative 1. So let's go ahead and put that there. Now we also know that to complete the graph, we can imagine a second function. Let's call it g of x. Now if we canceled out the x minus 2 in the top and the bottom, and we thought of g of x as equaling x minus 3, we recognize that that's the graph of a line. Now if we graph the line of g of x and we put a hole in it at 2 comma negative 1, then we will have the graph of f of x. We had to give it a different name because f of x equaling this function, which factors to this form, is not the same as g of x. It's almost the same as g of x. The graph of g of x and the graph of f of x are identical, except that f of x has a hole at the point 2, negative 1, and g of x would not have that hole. So now let's go ahead and make this graph. We know if we picked another x value, like 3, we would get the point 3 comma 0. So let's put that on here. And if we picked, say, 0 for x, we would get negative 3 for y. So we can plot that point. We know we're graphing a line, so let's go ahead and draw this graph. Now we have our graph of f of x, and we can go ahead and continue to analyze this function to explore limits. So what we need to do now is to create a table of values of f of x for x near 2. So we've got this table here that we're going to fill in. We know that our f of x is given, and we're looking for values as x approaches 2 from the left. So that's what these are: 1.9, 1.99, 1.999. Those are all getting closer and closer to 2, coming in from the left side of 2. And then we will look as x approaches 2 from the right. So 2.1, 2.01, 2.001. Those are getting closer and closer to 2, coming in from the right-hand side. So let's start by plugging in 1.9 into our f of x. So what I want you to do now is pause the video, grab your calculator, take the x value of 1.9 and plug it into f of x, and then write that function value here. Then restart the video when you're ready to check your answer. Now what I like to do when I know I'm going to be plugging in several values to the same function is I'm going to make use of the memory feature of the calculator. So first I will put 1.9 into my calculator, and I will store that in one of the locations. I'm going to pick memory location A. Hit enter. Now what I want to do is input memory variable A into our function. We will need to put a set of parentheses around our numerator. So open the left parenthesis, hit memory variable, we want A. We need to square that, then subtract 5 times memory variable A again, and then we need to add 6 and close with the right parenthesis. Then we will divide by the denominator, which also must be included inside a set of parentheses, and we need x minus 2, so we will put memory variable A minus 2, close your parentheses. Now we hit the enter button, and we see that f of 1.9 is negative 1.1. So let's enter that here. Now when I want to plug in x is equal to 1.99, I can do that easily on my calculator by taking 1.99, storing that into memory variable A. Now use the up cursor, get back to here where we already have that formula entered, and we can just hit enter, and we see that that next value is negative 1.01. Now pause the video, go ahead and evaluate these other four f of x values, then restart the video when you're ready to check your answers. When we plug x equals 1.999 into our f of x, you should have gotten negative 1.001. And now, as we analyze this table of values, as x approaches 2 from the left, the y values are getting closer and closer to negative 1. So we say that the limit from the left-hand side is that f of x approaches negative 1. Now, coming in from the right-hand side of 2, at 2.1, you should have gotten negative 0.9. Getting a little closer, 2.01, we get negative 0.99. Getting even closer, at 2.001, we get negative 0.999. Now, as x approaches 2, coming in from the right, we see that the y values are getting closer and closer and closer to negative 1. So we say the limit from the right is that f of x approaches negative 1. Now let's make sure that you understand how this table of values and these two limit values relate to the graph of f of x. Let's look first at the left-hand side. As x approaches 2 from the left, we see that the y values are getting closer and closer to negative 1, coming in from values that are below negative 1. And on the graph, that means as x gets closer and closer to 2, coming in from the left, you can see that the y values are getting closer and closer and closer to negative 1, coming in through values that are beneath negative 1. Whereas, as x approaches 2 from the right, we can see that the y values are approaching negative 1 through numbers that are slightly above negative 1. So on the graph right here, as we come into 2 from the right, the y values are decreasing down to negative 1. And that's how this table of values relates to the graph. Now we can use the values from the table to evaluate the limit. And we say that the limit as x approaches 2 of the quantity x squared minus 5x plus 6 over the quantity x minus 2 is equal to negative 1. And the reason that limit exists and is equal to negative 1 is because the limit from the left was exactly equal to the limit from the right. So when does a limit exist? If f of x approaches the same y value, L, as the x value approaches c from both the left and right directions, then the limit exists, and that limit is L. So relating that to our example that we just did, c is equal to 2. We were approaching 2 from the left and the right-hand sides. And from both sides, f of x approached negative 1. Whether we were coming in from the left of 2 or coming in from the right of 2, the y value was always approaching negative 1. So in our case, L was negative 1. So when the limit from the left is equal to the limit from the right, then we say that limit exists and is equal to the y value that you found, which is -1 in our example. And once again, here is that limit notation we just introduced. When you see these math symbols, you have two ways that you can read it. You can either say the limit of f of x as x approaches c is L, or you can say the limit as x approaches c of f of x is L. These two ways are equivalent to each other and are equally good. In this example, we have to sketch the graph of f of x equals the quantity x minus 4 over the quantity radical x minus 2. Graphing this rational function might at first look a little complicated, but if we apply a little bit of algebra, we can make it quite easy to do. Because I have radical x minus 2 in the denominator, that leads me to take this numerator and factor it using the difference of squares. We know that a squared minus b squared can factor into a plus b times a minus b. So we would get radical x plus 2 times radical x minus 2. Then we bring over this denominator, radical x minus 2. Now let's go ahead and evaluate f of 4. If we were to put 4 into the denominator, we see that we get 2 minus 2, which is 0. Can't have 0 in the denominator, so f of 4 is undefined, or we can say that it does not exist. Now we know that because we have this common factor here, that means we are going to have a hole in the graph of f of x, and that hole is going to be at x equals 4. And now to figure out the y value, what we can do is find a simpler function that agrees with f of x everywhere except at x equals 4. Because of this common factor, we could write g of x is equal to radical x plus 2, and we know that the graph of g of x will agree with the graph of f of x everywhere except where the denominator of f of x is 0, which is at x equals 4. So if we do g of 4, we would get square root of 4, which is 2, plus 2, so that's 4. So we know the hole exists at the point 4, 4. So we can come over to our graph, 4 on the x-axis, 4 on the y-axis. We know that there is a hole there. Now what we can do is just graph g of x, putting that hole in there, and we know that will give us the graph of f of x. So from our college algebra class, we know the basic shape of radical x. If we plug in a couple values, 0 for x, we get 2 for y, so we have the point 0, 2. If we put in a 1 for x, 1 plus 2 is 3, so we have 1, 3. And then we know the radical function has this basic shape. So there's our graph of f of x. It looks exactly like the graph of g of x, except that it will have the hole at the point 4, 4. Now what we are going to do is create a table of values of f of x for x near 4. And we're going to round to the 10,000ths place. So pause the video, go ahead and create your table of values. When you're ready to check your answers, restart the video. Coming in from the left-hand side of 4, we first plug in 3.9 and we get a y value of 3.9748. Now, if you didn't get that value, make sure that you double check that you put parentheses around your numerator and parentheses around your denominator. Plugging in 3.99, we get 3.9975. Plugging in 3.999, we get 3.9997. Now, coming in from the right of 4, when we plug in 4.1, we get 4.0248. At 4.01, we get 4.0025. And plugging in 4.001, we get 4.0002. Now, as we analyze this, coming in from the left of 4 on the x-axis means we're coming in this way. The y values are getting closer and closer and closer to 4 through numbers that are smaller than 4. So that's coming along here on the graph. So we see that the limit coming in from the left is 4. Now, coming in to x equals 4 from the right, we see that the y values, once again, are approaching y equals 4, coming in through numbers that are slightly bigger than 4. We can use the values from the table to evaluate the limit now. And we say that the limit, as x approaches 4, of the quantity x minus 4 over the quantity radical x minus 2 is equal to 4. And that's because we see that the limit coming in from the left was 4. And that's exactly equal to the same value we get for the limit coming in from the right. It's also 4. When the limit from the left is equal to the limit from the right, then the limit exists and is that same y value that you found coming in from both directions. Let's do a quick review of the greatest integer function. Greatest integer of x outputs the largest integer that is less than or equal to x. In this example, we have to find each value. So pause the video, try this one on your own, then restart when you're ready to check your answers. A tip when you're trying to evaluate the greatest integer of x is to place x on a number line and think of rounding down. So if we want to find the greatest integer of 1.5, put 1.5 on the number line, and then find the largest integer that's still less than or equal to 1.5, and we would round down to 1. The greatest integer of 0.999 repeating forever, if we put that on the number line, would be over here. And we have to find the largest integer that's less than that, so we would round down to 0. The greatest integer of 2.83 would round down to 2. The greatest integer of -3 would be -3, because -3 is less than or equal to -3. So that's the first one that's been equal to itself. The greatest integer of -0.4 would be right here, and that would round down to -1. And the greatest integer of -2.1 would round down to -3. In this example, we have to sketch the graph of f of x equals greatest integer of x. First, let's evaluate f of -1. So we know that the greatest integer of -1 is going to equal -1, because -1 is the largest integer that's less than, or in this case, equal to -1. So if we come over on the graph, we put in -1, we know that f of -1 is -1. And in fact, if we consider every x value between -1 and 0, we see that all of those are going to round down to -1. But as soon as we actually get to x equals 0, then it will jump up to 0. So that means every x value between -1 and 0 is going to output a y value of -1, but when we get to x equals 0, then it will hop up to a y value of 0. And then, of course, every x value between 0 and +1, so we don't actually get to 1, we get infinitely close to 1, we go to 0.99999, all of those x values are going to round down to 0. Put an open circle at x equals 1. Let's go ahead and label our axes here. And we can see that this behavior will repeat itself. Every x value between 1 and 2 in between is going to output a y value of 1, and then when we get to 2, it's going to jump up to 2, and then every x value between 2 and 3 will output 2, and so on. Over here on the negative side, the greatest integer of -2 is, of course, -2, and every x value between -2 and -1 will round down to -2. You can see why the greatest integer function is sometimes referred to as the step function, because it's like you're going up steps. So now let's create a table of values of f of x for x near -1. As we're coming in from the left, we know the greatest integer of -1.1 is going to round down to -2, and so will the greatest integer of -1.01 and -1.001. Now, coming in from the right, we know that the greatest integer of -0.9 is going to round down to -1, and so will -0.99 and -0.999. Now we can use the values from the table to evaluate the limit. Here we have the limit as x approaches -1 of greatest integer of x. And we have to say that this does not exist. And that's because the limit from the left does not equal the limit from the right. Now let's make sure you understand how this relates to the graph. As x approaches -1 from the left, all the y values are at -2, which is what this table of values is telling us. As x approaches -1 from the right, all of the y values are at -1. That's what this is telling us. So you can see that there's a big jump, and that the limit coming in from the left and the limit coming in from the right are going to two different places. Remember, for a limit to exist, the y value coming in from the left and the y value coming in from the right have to be the same number. And when they are not the same number, we have to say that that limit does not exist. In part 2, you will learn how to find limits from a graph. If the limit as x approaches c of f of x is equal to L, then f of x must approach L from both sides as x approaches c. In this example, you need to find each limit or function value from the graph or indicate that it does not exist. I'd like you to pause the video right now and use this y equals f of x to answer these two questions. Then restart when you're ready to check. First, we have to find f of -2. We see this is -1, -2 is here, and f of -2 has a y value of 3, so that means f of -2 equals 3. Now we have to find the limit as x approaches -2 of f of x. Now, coming in through x values to the left of -2, we see that the function has y values that are heading to 0 as we approach from the left. And as we come into x equals -2 from the right, the y values here are also approaching 0 as we come in from the right. Since f of x is approaching the same y value of 0 from both the left and right sides, that tells us that the limit as x approaches -2 of f of x is equal to 0. So notice that the function value at -2 is 3. The limit as x approaches -2 of f of x is 0. So the function value and the limit can be different values. Pause the video and try this next one, then restart when you're ready to check. First, we have to evaluate g of 1, and we can see that that is equal to 2. Then we have to look at the limit as x approaches 1 of g of x. Now, coming in from the left, we see that the y values are going to 2 as we come in from the left side of x equals 1. Coming in from the right, we see that the y values are also approaching 2 as x approaches 1 from the right. Since the limit from the left is going to 2 and the limit from the right is going to 2, we say that the limit as x approaches 1 of g of x is 2. So in this case, the function value and the limit were the same number. Next up, we are given this graph of y equals h of x. So pause the video and try answering this one and restart when you're ready to check. First, we have to find h of -1. Well, -1 is right here on the graph, and we see that the y value there, this is an open circle, so that isn't it. We have to go up here, and h of -1 is equal to 2. Now, to find the limit as x approaches -1 of h of x, we have to look at what happens as x approaches -1 from the left and x approaches -1 from the right. As the x values go into -1 from the left, we can see that we are writing along this part of the function. So the y value is approaching 2 as we approach -1 from the left. Whereas when x is approaching -1 from the right, we would be coming along this part of the function. So y is approaching -1 as x approaches -1 from the right. So since the limit coming in from the left is 2, which is different than the limit coming in from the right, which is -1, we have to say that the limit as x approaches -1 of h of x does not exist. And once again, that's because the limit from the left did not equal the limit from the right. Here, we're given the graph of y equals f of x. So pause the video to try answering these two and restart when you're ready. First, we have to find f of 2. Well, here's x equals 2. We see that we have a vertical asymptote there. So f of 2 does not exist, so you can either use the symbol for undefined or you can say does not exist. Both those answers are good. Now, to find the limit as x approaches 2 of f of x, we have to look at what's happening as x approaches 2 from the left and as x approaches 2 from the right. So coming into 2 from the left, we see we would be writing along this part of the function, and the y value there is going to infinity as x approaches 2 from the left. Coming in to the right of x equals 2, we would be on this part of the function, and once again, y is approaching infinity as x approaches 2 from the right. Now, the limit as x approaches 2 of f of x, coming from the left and coming from the right, we are getting the same answer, which is infinity, but really that means that the limit does not exist. Think about it this way. If you wanted to go shopping and your spending limit was infinity, then that means you don't have a spending limit. Your spending limit does not exist because you would be allowed to spend unlimited money. So for a limit to exist, it must be a finite number. It cannot be infinite, it must be finite. In this example, you are told to sketch a possible graph of a function with the given properties. So pause the video and see if you can make a graph to satisfy all 4 of those conditions. Then restart when you're ready to check. First up, we know that f of -2 equals -1. So that means there will be a point at -2, -1 on the graph. However, you cannot have drawn your graph coming into this point from either side. And the reason you can't have anything connecting right here is because the limit as x approaches -2 of f of x has to be 3. So that means as we are coming in to the left of -2 and coming in from the right of -2, our y values have to be approaching 3. So that would mean we would need something along the lines coming in from the left, coming in from the right. Now, maybe your graph came in from down here, or came in as a straight line, or came in curving this way, and that's all fine. But what you have to have is that coming in from the left and coming in from the right, both of them have the y values approaching 3. Now, let's look at this section over here. We are told that f of 3 does not exist. So that means we cannot have a point where the x value is 3. However, the limit as x approaches 3 of f of x is equal to 5. So that means as we come in from the left of 3 and we come in from the right of 3, our y values from both sides have to be approaching y equals 5. So then we could have an open circle here. Coming in from the left of 3, it's approaching y equals 5. Coming in from the right of 3, it has to approach y equals 5. So this is just one example. Your graph could have a different shape, but it would need to connect at these open circles. Yours may have come in here, gone through here, and come back down here. There's lots of variations that would work.